Oh, hello again. Welcome to another session of Learning Glass Studio, starring me, your host. So today we'll talk about crystal structure of silicon semiconductor metal. It's like a metal and non-metal, and if you dope it, it can do dope things in terms of controlling current, manipulating signal, doing all kinds of high-tech stuff. And it all starts with the structure of the solid. So it's silicon, it's an element, and that element is a solid at ambient conditions, and it can be amorphous or it can have a crystal structure. The crystal structure means it has a repeating lattice, a repeating pattern, and one important thing about many of the applications of this crystalline silicon structure is you take advantage of some of this phonon behavior. What is a phonon? Phonon has to do with the fact that a solid has many atoms together, and that interaction with the atoms gives them a vibrational mode of energy. So within the solid lattice, there's a vibration, and depending on how fast that vibration is, and you can assign a wave number to that frequency to quantify the energy, and that's a very important way to interact with a lot of the electrons and incoming light. So radiation has energy, radiation has a wavelength, radiation has a wave number that can come in and interact with a phonon that has a wave number and has energy. And that is how solar cells work for silicon. And then electrons, every thing has electrons. You can interact with these phonons potentially. So phonons are the vibrational mode. We'll talk about that. But first, let's talk about this actual lattice. Its crystal structure is a so-called diamond FCC lattice. It is face-centered cubic, but it's not the simple face-centered cubic. It's a diamond-like. So how does that look? Let me get my perspective game going and try to draw this out for you guys. So it's a cube, face-centered cubic, but it's not a simple cube. Let's see. So we'll give a flat perspective here. Nice new markers, that helps. So it's going to be like that. So this is the top part of the cube. Get my Bob Ross going. Like that is the top. Then get my perspective. This will be one of the faces. Goes down like this. Then complete the square to make a block. Just like that. So that's the start of this complicated thing. Okay, so then this is the cube of the lattice. This would be a unit cell consisting of multiple primitive cells. So I'll write that here. So this is the unit cell composed of multiple primitive cells. So I'll talk about what that means specifically next, but let me finish out this unit cell. So it's cubic, we drew the cube part. Now let's draw the diamond FCC. So F means face-centered, so there's one in the center, one silicon in the center of this here. This will be the green. Then there's one on this face back here. So there's one back here-ish. That's one of the silicons. There's one silicon on this center of this face. There's one on this center of this face. There's one in the center of this face on the bottom. So the sixth face has a silicon there. So those are the 6 silicons of the faces. Then there's some silicon on the nodes. So each of these, you get a silicon, you get a silicon, you get a silicon. I'm just color coding these different silicons just by the location. It's the same atom, same element, it's just a different location. So those are the 8 nodes on the vertices of this lattice. Now there's 4 others in the body. So what those would be, it's going to be pretty hard to do. So I'll just go for it. So let's say they're right here. It's not going to be perfect. It's very hard to draw this. So here, inside, somewhere inside the body, there's 2 of them. Let's connect these. They're not really connected, but I'll just draw it so that you guys can keep track of where I'm trying to do. So that's something, how this face-centered cubic diamond. So that's the unit cell. Then the primitive cell, I'll draw here. It's more like it's how this is composed when you can break this unit cell into a few of these primitive cells. Oops. So there's silicons there, and then there's one tetrahedral one here. So there's these vertices. And then there's one tetrahedral connection here. So that would be 8 and then 1 inside. So that's the primitive cell. That's the unit cell. And then, as we may or may not remember, that it's more convenient in some cases to describe this in terms of reciprocal space. So that is, where the Miller indices, because reciprocal space allows you to define the faces that cross-cut each of these orientations. And you can slice each of these, you can approach this unit cell by many different planes, and those different planes give you different faces, and reciprocal space helps you to keep track of those more conveniently in most cases. So, let me label this first. So this would be body. So this would be a silicon inside the body. This would be a silicon on the face-centered. And this would be on the vertex, the node. So that's a diamond FCC lattice. That's what silicon is in its crystalline unit cell. And then, if we were to apply this to a reciprocal lattice, in reciprocal space, we'll do a transform. And so the way that this coordinate system works is that from one of the nodes in the corner, like let's call this node 0, 0, 0, the reference point, you can draw out some axes. So this would be some axes R in the Z direction, some axes X, yeah, that's X. This is Y. But the actual, and another thing with this, we're going to label, is that you have the lattice constant so depending on the size of this unit cell, you have different size scales. This happens to be 0.543 nanometers. That's the lattice constant for a silicon unit cell. Okay, and then this is oriented, this is Z, X, Y, but then you can also have these lattice vectors, these vectors corresponding to the unit cell. That would go like that. Call this A1. So that's in the actual real space. And then if we go to reciprocal space, we'll find new vectors B by taking the transpose, or yeah, so just taking the reciprocal. So this vector, new vector B, the transpose of that is related to the inverse of the A vector. Right out of space here. So we're going to find a new vector by taking the inverse of the real vector in real space and that's how we get to reciprocal space, and that's going to look like this, similar but different, but reciprocal. So you just relabel the axes, so call it KZ, and then the lattice vectors look something like this. So the coordinates don't look too different. They're labeled differently because it's the reciprocal space. But what happens to the unit cell in reciprocal space, it goes from a face-centered cubic to a body-centered cubic. So that would look like this. Wrap my head around my drawing here. What am I trying to draw? Okay, there's one. Wait. My 3D perspective is hard to decipher here. Okay. Yeah. See what I was trying to do. So I'm going to try to draw this out. So this is face-centered cubic. Okay, so that's the difference. So if we were to take a similar perspective, this, like this back RZ could be the backbone, and this is like the node of the whole thing. So now the center of this axis is no longer one of the nodes like this. The center of the reciprocal space is in the body, and the way that would look would be something like this. Yeah, pretty much. Just go with this. No, more perspective. Something like that. Yeah. So you see how this kind of rotated? Something like that. So now the axes come from here. It's in the center now. So that's the reciprocal lattice of this silicon. It's now in reciprocal space. And then the question is, what is the reciprocal space of the primitive cell? That is called the Brillouin zone. And that's important. The whole point of all this was I wanted to show you guys what, I don't know if I spelled that right. There might be an extra I. So this Brillouin zone, I think I'm saying that right. It's French, of course, is the relationship. What that is actually, it's an actual, has a connection to the actual physical structure. But some of you may have heard of it. If not, you might see it in the context of solid state chemistry and interactions of these crystal structures with energy, with light, with electricity, with radiation. The way that you keep track of what's happening inside this crystal is first to ask what's happening inside the Brillouin zone. And that has an actual connection to the real space, and what it is, it's the reciprocal space of the primitive cell. So a primitive cell is smaller than the unit cell. So you can define some primitive cell based on this pattern of a crystal, and then the reciprocal space of that is the Brillouin zone. And in this case, for this diamond FCC lattice, you take the primitive cell and you take the reciprocal space of that. I'll just draw some quick shape. It looks something like this. It's like some hexagonal thing. And it has different faces. And what we're going to do is, now that we define these vectors, or so it has to do with these vectors here, these same vectors. And this is at a node. The backbone of this, so this will be here. The Brillouin zone, and it has looks like something like this. Not quite like a soccer ball, but almost. Stuff like that. So I'll draw it over here again. Okay, so all of this is like some crystallography stuff. And if I draw this more carefully here, let's draw this again. First, start off with a hexagon. That's one of the faces. Then another hexagon. It's going to curl up. Then another hexagon. And this is a square. Something like that. May have botched it. So I botched it a little bit. This should go like that. This should have a more of a full hexagon. Try to do some perspective artistry here. Something like that. So that's kind of what it will look like. This Brion zone, the reciprocal space of the primitive cell, and this is how you can think of the relationship between the crystal structure of a diamond lattice and a lot of solid state physics. What solid state physics? Electron interactions, light interactions, and other radiation interactions. And you can keep track of electrons' energy. And the way that you keep track of electrons' energy is that momentum. So electrons have momentum. Have energy and momentum. So the energy of the electron, of course, is, some, let's call it E of the electron. And the momentum, it's called K. I'll draw it. So the momentum, K, I'll call it K roughly, but it's really the wave vector of the momentum, and it has a certain energy. So you can assign momentum of this electron based on this physical lattice, this Brion zone, and it has certain orientations depending on the crystal structure. It has certain faces, and depending on where it is, this electron might have some momentum. So for this specific silicon lattice, in the center here, you can say that this is the gamma. I'll just define some locations. Let's say gamma is where this vector k equals 0. Let's call x, or chi, fancy x, is where this wave momentum, vector corresponding to momentum equals, what does it equal? Two pi over a. And then L, you can say this momentum vector equals negative 2 pi over a. So these are coordinates in k space. So now we've gone from real space, real three-dimensional x, y, z life. We've taken the reciprocal space where we can keep track of the faces more. And part of that reciprocal space is of the primitive cell. That's what the Brillouin zone is. And then we can start keeping track of the physics behind electrons and phonons based on momentum. And then we convert this reciprocal space to k space. Here are some examples of how that would work. And then if you actually draw it onto this Brillouin zone, if you go in this direction, so you start at 0, then this would be chi. And you go in this direction, this will be L. So that's what's physically happening. And then if you were to draw the band gap, so we've gone into reciprocal space, erase these. So this is a BCC lattice. Okay. We can draw the band structure of electrons in the Brillouin zone. What do I mean by band structure? I mean valence band versus conduction band. How does that look? It looks like this. It's similar to what we talked about in class, where we have, depending on the energy, you're either in the valence band or the conduction band. If these electrons get excited, they can potentially jump over the band gap into the conduction band. But in the Brillouin zone, we're going to specify where we are in reciprocal space. And then we convert that reciprocal space to momentum, k space. Okay? So we can draw a diagram where if this is gamma, we're literally here in reciprocal space in the crystal. Let me give me more space. No, I think that's enough. Yeah. So this is, no, I need more space. So in the center, it's gamma, and if you remember, k equals 0 here. If we go in this direction, we're going towards this fancy X chi. Little ribbons here. This space, this direction. And then if you reach chi, then your momentum increases to 2 pi over a, where a is your lattice constant. Then if you go in the other direction towards L, your momentum so then on the x-axis, we know that which band you are depends on how much energy you have. So the lower energy is for the electrons in their normal ground state electron valence cloud. But if you give them more energy somehow, they can skip the band gap and go into the conduction band. So that depends on how much energy the system has or is given somehow. So the scale would be 0, so this would be 4 electron volts, 3, 2, 1, -1, -2 electron volts. Some reference point 0. So if you are, depending on where you are, these energies might be different. So this is keeping into account the momentum of your electron and the energy of your electrons. And the momentum literally depends on where you are in this crystal structure. So this is kind of a momentum axis here. In K space. Okay. So how does this look? Well, looks something like this. Let's draw a line at 0. Then relative to that, you have this peak at 0 momentum, and it goes like that. That's the valence band. The valence. This is the ground state where the electrons sit normally without any excitation. But there is an available state that is not naturally there for silicon, but it's possible if you were to somehow interact with this silicon, either injecting an electron in through some voltage, applied voltage, or interaction with light, some electromagnetic interactions, you can access this other energy state, which is known to look like this. So this would be a gap, but interestingly, it goes like that. So this is the conduction band. And this band gap that we've been talking about, it actually has a second dimension, momentum. So this is the band gap, and so that's like the minimum difference. Of course, there's a huge difference here, but you could potentially make a smaller difference here. You can jump from the valence band over the gap to the conduction band, but you'll have a different momentum. So note here, for silicon, this is for silicon. Depending on your material, you have a different structure, different profiles. So for silicon, the wave, the momentum vector k of the valence max, the highest occupied molecular orbital, does not equal the lowest unoccupied molecular orbital, the conduction min. So there is a gap there, and the smallest gap is not the same momentum. So that's important for a reason we'll talk about next. So the point here is that if you want to act across this band gap with the minimal amount of energy, you have to get momentum involved. That's the point. Excuse me. Okay, so I'll erase this stuff and remind you some other way. Should I erase? Yeah. So we are in reciprocal space. Do it over here. Lattice constant A. So then what we did was we took the reciprocal space of the primitive cell, the reciprocal lattice of the primitive cell. That's what gave us the Brion zone, and we can picture it through this structure here. It has some physical space. And then we convert it to a momentum space, K space. That allows us to quantify what the band gap is between the valence band and the conduction band, which allows you to behave like, in the solar cell, create a circuit across this material. You need a conduction. And then, so the next phase of that, if we're talking about solar cells, how do we do this? How do we cross this band gap when there's different momentums? Well, the missing link is that there's other subatomic particles. So sub-electrons are one subatomic particle. You have electrons, you have protons at the nucleus, and you have neutrons, but also and phonons. What are phonons? Phonons are the vibrational mode of this structure. It's specific to a solid structure, where it is the energy and the momentum of the phonon comes from the vibrational mode. So it's kind of an abstract thing, but you can still consider it to be a subatomic particles. And the math works behind it. So phonons are vibrational modes of solids. But they can be treated as particles because phonons have energy E phonon, and momentum. Again, momentum is, I have it here actually. The momentum, so this is the K space. It's related to K, but it's actually, you need a Planck's constant there. It's momentum Planck's constant over 2 pi, and then the wave vector. That's the momentum of a phonon. And so phonons, they are important for many things because in heat transfer, if you go deep into the solid state physics, you identify for heat transfer by this fundamental atomic scale analysis, you would go into the Brion zone, take the reciprocal space of the primitive lattice, and then you can use phonons to quantify heat transfer. So phonons participate in heat transfer. If these are vibrational modes, that's a way to transfer energy across the mass by heat transfer. So phonons participate in that through these collisions of energy and mass. So phonons participate in heat transfer. So they have energy and momentum. Heat transfer and light generated carrier, light generated carriers and carrier recombination. What are carriers? Well, if you remember from our semiconductor discussions, you need charge to go in and out. So this charge can be carried by a positive holes or negative electrons. So this means either positive or negative current, or positive or negative transport. And for all semiconductors, they operate by manipulating a depletion layer, meaning that you design it to be doped with excess holes or excess electrons, and you create a junction so that on either side you have these excesses, and then within that junction you recombine these excess electrons and holes. So when they recombine, they form this depletion layer, and that induces a voltage, and then you manipulate that whole structure to get what you want, to control which direction current goes, to turn current on and off, to switch things up and down. That's what a semiconductor circuit would be. These field effect transistors work like, but you use similar physics so that when, in the case of a solar cell, you can use the material properties to interact with light. It can excite these electrons in the conduction band, and then phonons become involved as well. So how do phonons become involved? That's a good question. So we're in K space. Do I erase this nice lattice? Yeah. So I'll keep the primitive cell. So here's the beautiful physical space that we can touch and feel and look under the microscope to see this. Then we go to reciprocal space, which is easier to keep track of the faces. And then when we take the reciprocal space of a primitive cell, that's the Brillouin zone, and that's how you can keep track of a lot of the physics, is where it is in the Brillouin zone, because that's like the building block of this whole lattice. And if you can keep track of the building block of the whole lattice, that'll give you some idea of what the behavior is. So, by the K selection rule, the wave vector selection rule says that so when we're trying to manipulate the behavior of the electrons, in the case of silicon, you need to have some momentum change, because this minimum gap is a distance of the gap, but the actual other axis momentum is different. So you need to also, it's not only jumping the gap in energy, you also have to change the momentum as well. So you can do that, you can change the momentum with an electron-phonon collision, because as we just, so the phonon has momentum, the electron has momentum. So the Planck's constant over 2 pi, that's the momentum of an electron. So if you want to move the momentum of an electron, you can do this by collisions or interactions with the phonons. So when you do that, you follow the conservation of energy and momentum. So we all know about the conservation of energy and momentum, but the K selection rule is different in the sense, the only difference is that to begin with, energy is quantized and momentum is quantized. We're talking about atomic behavior, so there's these allowed energies depending on the structure, and anything in between here does not happen. It's separated out. And because it's a solid, it's kind of smeared, so it becomes a band rather than clean steps. So it's a smeared band, but nonetheless, there's still some forbidden energy in between there. That's where the K selection rule is. It's saying that you already know that you have a certain energy and you have a certain momentum, but not all energies are possible. So then when you go and combine, when you conserve the energy and momentum, you already rule out certain combinations. Like, it's not going to have this energy in between the band gap and so forth. So that's the K selection rule. It's saying that when you do have this collision, it's also restricted by these quantum-like behaviors. Okay, so that's what I just said. Then we can then also keep track of the band structure of phonons. So silicon, phonon, band structure. This is the vibrational mode of a solid, and you can also draw this in terms of K-space. So the important ones here would be for gamma and chi. So here's gamma. Here the momentum vector is 0. This is chi. Here the momentum vector is 2 pi over A, where A is a lattice constant. So the bigger the crystal, the more momentum this has. And so this is phonon energy. It's still energy, it's just belongs to the phonons. That's in electron volts. And let's say that this is 0.06. Oh, that was nice. So 6, 5, 4, 3, 2, 0.01. And this is the momentum wave vectors. So if you start in the center at gamma and you go towards chi, the phonon energies will increase like this. But there's 4 different types of phonon energies. So this is the so-called transverse acoustic mode. So phonons are vibrational modes of solids. One mode of this solid is called, phonons are the vibrational modes of solids. One vibrational mode of silicon is called the transverse acoustic mode, and the reason why it's called acoustic is because humans can hear it. So this silicon, if if it were to make some sounds and vibrate, it will be to this phonon energy here. And so that's why it's called acoustic, and it can be transverse versus longitudinal. That's a different story. So here's the longitudinal side. It goes something like this. This will be the longitudinal acoustic. And then you have something like this. This would be the longitudinal optical. So in terms of some vibrational mode, this is called optical because it behaves in some interactions with light. This is what is the relevant vibrational mode for that case. And then this would be the transverse. So if we're talking about interactions with light with a solar cell, the phonons for silicon come into play, and they can interact light with this momentum and these energies. So that is kind of like the situation when you have light coming into silicon. That light at a given energy, at a given wavelength, can interact with these vibrational modes and these electrons according to this energy. So the whole point of this is that to induce conduction in this silicon, you have to cross this band gap, and this band gap occurs at a different momentum, so the phonons get involved so that they supply this momentum due to this conservation of the case selection rule, conservation of energy and momentum. So how do you get here? Well, phonons come in. Why do you need phonons? Because light, photons, interestingly, so just the way that Mother Nature works, interestingly, the momentum of a photon is 0. The momentum of a phonon is non-zero. The momentum of the electrons are non-zero. So that's where phonons come in. If you want to get electricity from the sun, that is a flux of electrons coming in, of photons, so it's some energy coming in by photons. Those photons have energy, but they don't have momentum. So if you want to cross this band gap with silicon, and you need to change the energy, which can come from the photons, but you also need to change the momentum. Where does that come from? Some interactions with phonons. And to get into all the math, you have to know what these energies are according to the place on the structure and so forth. So that's a whole different story. We're not going to get into that, but hopefully this was a quick crash course on how the crystal structure of silicon affects the physical behavior. It's the crystal structure and the silicon itself, because once you get into that crystal structure, that tells you where it is in space. That's where these reciprocal spaces are keeping track of. But then this actual energies depends on how many electrons you have and so forth, and what the atom structure is. So the atom structure has to do with kind of like this, these energies, but then the crystal structure tells you something about how it interacts, how these behavior changes in the solid. Then, for this momentum factor that comes in, you have to also consider phonons. Excuse me, because that's a way to get this change in momentum, because light does not have momentum. Photons do not have momentum. Okay, so that was a quick crash course. Thank you, and I'll see you next time, if not some other time. Okay, thank you.